Hi, geometry scholars. Welcome to chapter 9. This is a super important chapter. It's going to be a very big basis for what you're going to do in Algebra 2. And the good thing is you already know part of it. So this first section is on, as you can see, what you will learn, the Pythagorean Theorem. Use the converse of the Pythagorean Theorem and also classify triangles. So you already know how to do this stuff. We're gonna fly through section 1, and I look forward to reminding you about a bunch of stuff you already know. So let's go. First, we're going to start off with one of the most famous theorems in mathematics, which is known as the Pythagorean Theorem. Named for the ancient Greek mathematician Pythagoras, this theorem describes the relationship between the side lengths of a right triangle. Remember, only a right triangle. So the theorem says, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. We usually think of it as a squared plus b squared equals c squared. So when we look at the problems, we can sometimes figure these out in our head. These are really, really helpful things called a Pythagorean triple. So it's a set of three positive numbers, a, b, and c, that satisfy this equation. The most famous and the one that's easily recognizable is 3, 4, 5. If you have two legs that are 3 and 4, then the hypotenuse is 5. And so any multiple of 3, of a leg of 3, a leg of 4, and a hypotenuse of 5, you can figure out just by memorizing that triple. 5, 12, 13 is another one, 8, 15, 17, and 7, 24, 25. So those are the most common, but then as you can see multiples underneath them, you can use those triples to write proportions and solve for x pretty easily. This study tip's a really good one too. You may find it helpful to memorize these, shown in bold, because standardized tests uses them. And anytime you can shave off a little time on a standardized test is always good. Plus, you use your calculator, less. All right, so here's what we do. We're going to use the Pythagorean theorem, show you an example.
Find the value of x. Then tell whether the side lengths form a Pythagorean triple. Solution. First, write the Pythagorean theorem, c squared equals a squared plus b squared. In this right triangle, the length of the hypotenuse is x, and the lengths of the legs are 5 and 12. So, substitute x for c, 5 for a, and 12 for b. Now, 5 squared is 25, and 12 squared is 144. 25 plus 144 is 169. So, you have the equation x squared equals 169. To solve for x, find the positive square root of each side of the equation. This gives you x equals 13. So, the value of x is 13. Because the side lengths 5, 12, and 13 are integers that satisfy the equation c squared equals a squared plus b squared, they form a Pythagorean triple.
So I don't know if it was in that first list, but that's another Pythagorean triple that you can put in your little tool bag for solving math problems like this. So I think we have a second example here. Boom.
Find the value of x. Then tell whether the side lengths form a Pythagorean triple. Solution. First, write the Pythagorean theorem, c squared equals a squared plus b squared. In this right triangle, the length of the hypotenuse is 14, and the lengths of the legs are 7 and x. So, substitute 14 for c, 7 for a, and x for b. Now, 14 squared is 196, and 7 squared is 49. So, you have the equation 196 equals 49 plus x squared. To solve for x, first subtract 49 from each side of the equation. This gives you 147 equals x squared. Then find the positive square root of each side of the equation. This gives you the square root of 147 equals x. To write your answer in simplest form, you can first use the product property of square roots to write the square root of 147 as the square root of 49 times the square root of 3. When you simplify, you get 7 times the square root of 3 equals x. So, the value of x is 7 times the square root of 3. Because 7 times the square root of 3 is not an integer, the side lengths do not form a Pythagorean triple.
And the difference, of course, in this problem as opposed to the last one is you were given the hypotenuse, not one of the legs. So it makes a little bit of a difference in how it's solved. Here we go. Here's one that's a real life problem. Again, very useful.
The skyscrapers shown are connected by a skywalk with support beams. Use the Pythagorean Theorem to approximate the length of each support beam. Solution. Each support beam forms the hypotenuse of a right triangle. The right triangles are congruent, so the support beams are the same length. By the Pythagorean Theorem, x squared equals 23 and 26/100 squared plus 47 and 57/100 squared. Next, find the positive square root of each side of the equation. This gives you x equals the square root of the quantity 23 and 26/100 squared plus 47 and 57/100 squared. Using a calculator, you get x is approximately equal to 52 and 95/100. So, the length of each support beam is about 52 and 95/100 meters.
So one thing I was going to tell you, this whole chapter is a lot of calculations. So make sure you have a calculator nearby. Okay. So we're going to do some of these examples in class together. We also have the converse, which means the converse of the Pythagorean is also true. You can use it to determine if a triangle with given side lengths is a right triangle, because if it is a right triangle, it will meet those conditions. So here's the converse. If the square of the length of the longest side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. So if c squared equals a squared plus b squared, then ABC is a right triangle. There's a proof of that, example 39 in your book, but we're just going to go ahead and use it. Verifying right triangles. Here's one way to do it.
Tell whether each triangle is a right triangle. Solution. Use the converse of the Pythagorean Theorem. Let C represent the length of the longest side of the triangle. Check to see whether the side lengths satisfy the equation c squared equals a squared plus b squared. Part A. Use a calculator to determine that the square root of 113, which is approximately equal to 10 and 630 thousandths, is the length of the longest side in Part A. So, substitute the square root of 113 for C, 7 for A, and 8 for B. Now, the quantity the square root of 113 squared is 113, 7 squared is 49, and 8 squared is 64. 49 plus 64 is 113. 113 equals 113. So, because the side lengths satisfy the equation c squared equals a squared plus b squared, the triangle is a right triangle. Part B. The length of the longest side is 4 times the square root of 95. So, substitute 4 times the square root of 95 for C, 15 for A, and 36 for B. Next, notice that the quantity 4 times the square root of 95 squared can be rewritten as 4 squared times the quantity the square root of 95 squared. Now, 4 squared is 16, the quantity the square root of 95 squared is 95, 15 squared is 225, and 36 squared is 1,296. Then, 16 times 95 is 1,520, and 225 plus 1,296 is 1,521, which is not equal to 1,520. So, because the side lengths do not satisfy the equation c squared equals a squared plus b squared, the triangle is not a right triangle.
So A is and B isn't. We're just going to do one more way to use the Pythagorean theorem now, and that is we're going to classify triangles. So when I say classify, we're going to either say if they aren't right, then they're either acute or obtuse. So let's remind ourselves what that is. Acute means that all three angles are less than 90 degrees. Obtuse means at least one angle is larger than 90 degrees. So remember, it all has to do with that right angle. So it's either less than 90 or more than 90. So it all has to do with the hypotenuse. If you look, this is the theorem 9.3 for any triangle ABC, where C is the length of the longest side. So we would call it hypotenuse if it were in a right triangle, because the hypotenuse is always from the right angle. Otherwise, these are not across from 90 degrees, so we can't call them hypotenuses, but we can call them the longest side. So if your c squared, if your longest side is less than the two other sides squared, a squared plus b squared, then ABC is acute. That means it's smaller than 90. If c squared, the longest side, is greater than a squared plus b squared, then ABC is obtuse, because C, the angle C, has to be greater than 90 degrees. So you can classify a triangle if it's got a right angle, it's a right triangle. If the longer side is less than 90, it's acute. If the longer side is greater than 90, it is obtuse. Here we go. We're just going to do a couple of examples here and verify these segments.
Verify that segments with lengths of 4 and 3/10 feet, 5 and 2/10 feet, and 6 and 1/10 feet form a triangle. Is the triangle acute, right, or obtuse? Solution. Step 1. Use the triangle inequality theorem to verify that the segments form a triangle. Remember, the triangle inequality theorem states that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. First, check to see whether 4 and 3/10 plus 5 and 2/10 is greater than 6 and 1/10. 4 and 3/10 plus 5 and 2/10 is 9 and 5/10, which is greater than 6 and 1/10. Next, check to see whether 4 and 3/10 plus 6 and 1/10 is greater than 5 and 2/10. 4 and 3/10 plus 6 and 1/10 is 10 and 4/10, which is greater than 5 and 2/10. Finally, check to see whether 5 and 2/10 plus 6 and 1/10 is greater than 4 and 3/10. 5 and 2/10 plus 6 and 1/10 is 11 and 3/10, which is greater than 4 and 3/10. So, because the sum of the lengths of any two sides is greater than the length of the third side, the segments with lengths of 4 and 3/10 feet, 5 and 2/10 feet, and 6 and 1/10 feet form a triangle. Step 2. Classify the triangle by comparing the square of the length of the longest side with the sum of the squares of the lengths of the other two sides. So, compare c squared with a squared plus b squared. The length of the longest side is 6 and 1/10 feet. So substitute 6 and 1/10 for C, 4 and 3/10 for A, and 5 and 2/10 for B. Now, 6 and 1/10 squared is 37 and 21/100. 4 and 3/10 squared is 18 and 49/100. And 5 and 2/10 squared is 27 and 400. 18 and 49/100 plus 27 and 400 is 45 and 53/100. 37 and 21/100 is less than 45 and 53/100. So, because c squared is less than a squared plus b squared, the segments with lengths of 4 and 3/10 feet, 5 and 2/10 feet, and 6 and 1/10 feet form an acute triangle.
Hopefully you follow those steps. 2 parts. First, verify its triangle. Second, classify what it is. Again, we'll do a couple of examples under the camera in class. Otherwise, you're ready to start your exercises, and this will be a quick section. So, done with our video.